Look at this shot. A sports car drifting through heavy rain with physically accurate water splashes and perfect consistency. For years, standard AI video generation has struggled with this exact scenario, usually producing random, jelly-like morphing instead of solid objects. So how do these new videos hold together so well? If you take a standard raw AI model and ask for a complex sequence, you often get a mess. The physics break down, and objects lose their permanence. This jump in quality stems from engineering a multi-layered production pipeline, moving beyond the capabilities of any single generative model. Historically, standard text-to-video models operated like a black box. You feed them a prompt, and they try to calculate lighting and complex physics, the virtual camera movement, and the character's identity, all at exactly the same time. Because these systems treat motion as a side effect of de-blurring noise frame by frame, small mathematical errors stack up quickly. By frame 50, those tiny miscalculations have snowballed into massive visual hallucinations. To fix this, modern systems break the generation process apart into a sequenced, decoupled pipeline. Instead of asking one model to guess everything, they isolate the variables. By mathematically restricting the AI's options before a single pixel is drawn, these pipelines force the model to stay on script and stop hallucinating. At the base of this pipeline is the core engine, the Latent Diffusion Transformer, or DIT. This architecture replaces the older 2D networks that struggle to track objects over time. A 3D variational autoencoder compresses raw video into a dense latent space. This block is sliced into space-time tokens, calculating spatial and temporal relationships simultaneously. Modern engines then use rectified flow, a direct, straight-line path from noise to final frame, suppressing the drift that causes morphing. While this new baseline engine provides incredibly stable motion, it still requires strict directorial guidance to produce actual cinema. That guidance starts before any image generation occurs, in what's known as the cinematic logic layer. When a user types a simple, vague idea, a large language model steps in as an automated director. It expands that basic prompt into a highly structured plan, defining a specific shot list, lighting setup, and pacing guide. A short text prompt contains high entropy. There are millions of ways the AI could interpret it. A structured pre-production plan eliminates that guesswork. By resolving that ambiguity up front, the system steers the diffusion process into a much tighter, more predictable probability space before the first pixel is sampled. Once the plan is set, the pipeline applies geometric conditioning. This solves a major headache by completely separating the movement of the virtual camera from the movement of the subject. To make those camera moves look authentic, the system draws on optical priors, learning from the physical properties of cinema cameras, like this ARRI Alexa. This allows it to accurately simulate physical lens distortion, anamorphic stretch, and realistic depth of field. The virtual camera's path is calculated using Plücker ray parameterization, projecting 6-dimensional vectors onto the scene. By enforcing epipolar geometry, foreground and background perspective shifts are locked mathematically as rigid body transformations, ensuring they don't warp or blend during pans. The AI isn't guessing what a tracking shot might look like, it is rendering a flawless mathematical projection. Even with a perfect camera move, you still have to deal with the hardest problem in AI video, character drift, where a subject's facial features warp across cuts. The solution is a technique called Decoupled Cross-Attention. It mathematically severs the character's identity data from the data describing the action in the scene. A vision model extracts a permanent identity embedding from reference images. These identity tokens are routed down an isolated path, bypassing the dynamic action prompt. When injected into the final generation layer, the environment alters, but the subject's facial landmarks remain mathematically locked. With this architecture in place, the system is no longer trying to generate a plausible random person. It is rendering a specific, permanent digital asset. For the actual pixel generation, platforms like Higgsfield act as a multi-model router. Instead of forcing one system to do everything, they assign tasks to specialized engines, routing to Kling for movement or CDance for synchronized audio. Finally, the output goes through a cascaded super-resolution pipeline. To keep the physics coherent, The base generative model only calculates the scene's global motion at a very low resolution. Once the motion is locked in, a dedicated temporal upscaler steps in. It follows the optical flow fields from that first pass to synthesize high-frequency details, filling in skin pores, fabric weaves, and atmospheric lighting. By calculating broad physical movements first and saving fine texture rendering for a separate step, the pipeline eliminates the high-frequency pixel noise that causes flickering. Producing cinematic AI video relies entirely on this rigorous orchestration. It takes a logic layer for reasoning, strict geometric conditioning for the camera, and isolated memory banks for identity, all tied together by a router. The highest quality content emerges when platforms build a complete digital film studio architecture around the AI, controlling its output through external constraints. So, the next time you see a remarkably perfect AI-generated sequence, ask yourself, are you just looking at the output of a single AI model, or a specific, highly engineered orchestration pipeline?